mass composition. So, look at this problem. You are to prepare 2.50 times 10 squared grams of 7.00% by mass sodium carbonate solution. What mass in grams of sodium carbonate and what volume in milliliters of water do you use? And so we want 250 grams of this solution. And the solution is going to be 7.00% by mass sodium carbonate. And so what that means is what? 7.00% by mass sodium carbonate means what? So we should write this as a conversion factor. How would you write it? Conversion factor. Well, we would just write it like this: 7.00 grams of sodium carbonate, pure sodium carbonate, for every 100 grams total. And so the total we just call it solution, or sodium carbonate solution. So that's probably more descriptive. Because we have to be careful. Are we talking about sodium carbonate pure, or are we talking about sodium carbonate mixed, which is the solution? And the solution is the total thing, so this is per 100 grams of sodium carbonate solution. So if I have 200 grams, actually we could do this in our heads. If I have 200 grams of solution, how many grams of sodium carbonate? 14. If I have 250 grams, well, how many grams of sodium carbonate? Well, that'd be 14 plus half of this, which would be 3.5. So it'd be 17.5 grams of sodium carbonate. So let's see, is that right? 17.5 grams of sodium carbonate. Yeah, that's right, actually. So we were able to do it in our heads. If we don't want to do it in our heads, what we'll do is we'll just do the dimensional analysis. Sometimes we aren't given nice clean numbers like 250 grams, you know. Sometimes we're given odd numbers, lots of decimal places. So it's much easier to do this by dimensional analysis. By dimensional analysis, we just use our given. Our given is going to be 250 grams of sodium carbonate solution, which is a mixture. And we want to figure out how many grams of pure sodium carbonate there are. And so we know the ratio, 7.00 grams of pure sodium carbonate for every 100 grams of the solution. What do they call it? They called it solution. I'm going to call it sodium carbonate solution, just to emphasize the difference here. And so the grams of sodium carbonate solution cancel, and that gives us grams of pure sodium carbonate, which comes out to 17.5 grams of pure sodium carbonate. Well, how much water is there then? Well, if we have 250 grams total, you know, the grams of solution, that is, the grams of sodium carbonate solution will equal the grams of pure sodium carbonate plus the grams of water. And so here, this is 250 grams. The grams of pure sodium carbonate, which is calculated as 17.5 grams. And so this is our unknown. And so these two have to add up to 250 because the mixture only has two components. The mixture has sodium carbonate and water. You take pure sodium carbonate and pure water, and you're going to make this homogeneous mixture, which we call a solution. And so how many grams is this? It would be, can you see it? It's going to be what plus 17.5 will equal 250? Yeah. And so let's take a look. Well, they rounded it, of course. They rounded it to 233, but it should be 232.5. Otherwise, you're going to get more than 250 grams. And that would lead to some round off error. How many milliliters is that? Well, we know the density. The density of water is 1.0 or 1.00 grams per milliliter. And so if it's 233 grams, it's 233 milliliters. We We always do that, you know. Grams and milliliters are going to be the same for water. And so we'll add 233 milliliters. To 2 sig figs. To more than 2 sig figs, then we got to start worrying. Are grams and milliliters the same? No. You go 3, 4 sig figs, then we don't want to use this. Well, 3 sig figs here, we're okay. 4 sig figs, we start worrying. All right, that's percent by mass composition. We also have percent by volume. You know, alcohol solutions sometimes are percent by volume. We're talking about percents, so let's do that. This would be for liquid solutions. And so we have percent composition by volume. Volume percent. For example, air. You know, what's the volume percent of nitrogen in air? It's about 80%. Right? Volume percent oxygen in air is 20%. But we could do that for alcohol solutions as well. You know, it might be 50% by volume ethanol. You know, stuff like that. And so we have percent by volume. Percent by volume is just the volume of the solute. Okay, this is typically for liquids or gas. If it's a solid, it doesn't quite work so well, you know, because solids volume changes quite a lot when you break up the crystal. And so it's going to be the volume of the solute, liquid or gas, over the total volume. In other words, the volume of the solution. Total volume. Volume of solution. So let's skip over that here. So percent by volume. We can also have percent by pressure. You know, that's another way of expressing, but that's just for gases only. Probably for liquids, what's the most common? Liquids, the most common are percent by volume, percent by mass, and this one. This is called molarity. This is what we were doing in the lab the other day. We're trying to determine the molarity. Molarity is a different way of representing the concentration or the composition of the solution by taking the moles of solute, dividing by the liters of solution. Molarity is very handy for stoichiometry. In fact, molarity is the #1 way we're going to express the composition of a mixture of a solution for liquids. So this is the definition: moles of solute per liter of solution. Calculate the molarity of a solution made by dissolving 15 grams of sodium hydroxide and diluting it to 1.00 times 10 squared milliliters. This is typically what's done with molarity. Because 15 grams of sodium hydroxide, do you know what the volume of that is? 15 grams of solid sodium hydroxide. You know what the volume of that is? No, I guess we could get the density and everything else, but will the volume still be the same if you take the crystals of sodium hydroxide, dissolve them in water? Let's say you took 2 milliliters of sodium hydroxide crystals. You dissolve those in water. Are they still going to occupy 2 milliliters of space? It turns out no, they aren't. They're going to occupy a different amount of space because the crystals have the crystals, the way they pack, there's empty space around certain things. It all depends on how things pack together. And so this is different than the last problem. And one of the key differences is how they state how much water they're adding. How much water? How many milliliters of water are they adding to this? In the last problem, we had to add 233 or 232.5 milliliters of water. In this problem, how many milliliters of water are they adding? They don't say. And they aren't going to say. They aren't going to say it because it's very tricky because of what happens with the volumes when solids dissolve. Even when liquids dissolve, we have to be careful because sometimes the volumes aren't additive depending on how they pack together. And so in this particular problem, how do they say it? How they say it is they add water until the total volume hits 100 milliliters. Do you see that? And so however much water they need to add, that's how much water they add. And so let's take a look at this. So the molarity of the sodium hydroxide, we need to know the moles of sodium hydroxide, pure sodium hydroxide, over the liters of sodium hydroxide solution. The liters of sodium hydroxide solution is okay. I mean, we have 100 milliliters, and then we just convert it into liters because that's the total volume of the solution mixture. And so the volume would be 0.100 liters, 3 sig figs. But what about the moles of sodium hydroxide? The moles of sodium hydroxide we're just going to get from stoichiometry. You know, we can calculate the moles because if we know the grams, we can just do a gram to mole conversion. If we got 15 grams of sodium hydroxide, we just convert that to moles of sodium hydroxide. Using the molar mass, you know, flip over the molar mass and we'll have it. So let's see what they did here. The molar mass is 40.00 grams per mole. So they're going to convert it to get moles. So 15 the grams of sodium hydroxide cancel, that gives us moles. So we have 0.38. I don't round here like that would be an intermediate rounding step. I prefer not to do those. So let me recalculate that number without doing the intermediate round. Or you just carry all the digits in your calculator. The best is just to leave it in your calculator. So that would be 15 divided by 40. 0.375. So I would get 0.375 here. In chemistry, you're not supposed to do these kind of intermediate rounding steps because if you have a very long calculation, by the end of that calculation, you could be extremely far off if all the roundings went in one direction. And so what we're going to have is we're going to have 0.375 moles of sodium hydroxide, pure sodium hydroxide, over 0.100 liter. And so divided by 0.100, this is going to give me 3.75 molar. And we use a capital M here, sodium hydroxide. So what we got here. Yeah. And then we could round that now. We could round that to 2 sig figs. We're only allowed 2 sig figs. This is going to round to 3.8 molar sodium hydroxide. So that's a molarity. Molality is not used as often. Molality is used for something called colligative properties. Colligative properties you might have heard before, like osmotic pressure. Actually, molarity is used for osmotic pressure. Let me take that back. It's used for something called boiling point, elevation, and freezing point depression. We'll talk about those at the end. And so molality is just pretty much used for that. But there's one advantage molality has over molarity, and that is it doesn't change with temperature. Molarity changes with temperature because liquids expand and contract with temperature. So if the liquid expands, you're doing it per liter. And so if the volume grows, then the concentration goes down. In cold weather, it contracts, concentration goes up. And so molality solves that because does kilograms expand or contract with temperature? You have 1 kilogram, does it become 2 kilograms at hot temperature, or half a kilogram at cold temperature, or vice versa? No. And so the kilograms, the quantity of matter is not going to change. It could expand or contract, but that's not going to change how much it weighs. And so that's a big advantage of molality. We'll do a molality calculation when it's absolutely necessary, but the definition is moles of solute. Now this is different because, in typical we do total out of the total. This is not the total. It's the component A divided by the total. But this is component A divided by just the solvent. And so it's per kilogram of solvent. So that's another unique thing about molality. And so let's skip this calculation here because we're just going to do molality when we get to the colligative. We're going to look at normality, completely skip normality. Normality is if you do tons of titration. and it makes your calculations a little bit easier, maybe. But normality, skip that. So the key ones are the first two. Actually, this molarity is the big one, and then percent. Either percent by mass or percent by volume. Those are two big ones for liquid solutions. Molality, nah, except for a couple of calculations. Normality, nothing. We're not going to do anything for normality. All right, let's figure out the composition. But you know, when you buy, let's say you buy some cleaners or you buy some juice, you know, you could buy the concentrated stuff and then dilute it, or you can buy the pre-diluted stuff. You know, what do you get usually? The concentrated stuff and then dilute it yourself, or the pre-diluted stuff you can just use straight. Well, using the pre-diluted stuff is a lot more convenient because you don't have to do a solution dilution. Solution dilution is a bit of hassle. I buy concentrated. Some cleaners I buy it concentrated and then dilute it myself. It saves a little bit of money, but in chemistry we do that. We buy concentrated stuff and then dilute it. When you buy concentrated stuff and dilute it, we want to do a simple calculation to figure out what the new concentration is. And so this is called solution dilution. Solution dilution is we are going to dilute a concentrated solution because that's, you know, when we buy, let's say we buy HCl. You know, let's say we need 0.1 molar HCl. We could buy the 0.1 molar HCl, but the shipping charge is going to kill you. And so rather than buying 0.1 molar HCl, we buy the 18 molar stuff. You know. The 18 molar, we don't need that for the lab, so we end up diluting it way down. Dilute would be like 6 molar, you know, HCl. That'd be dilute, or 0.1 molar. And so the solution dilution equation is going to look like this. You know, when we do this, the molarity of the dilute solution is equal to this. It's the volume of the concentrated solution over the volume of the dilute solution. This is called the dilution factor. And so let's say we take 1 part concentrated and make it 2 parts total. If we take 1 part and make it 2 parts total, that is, you know, we dilute it by a factor of 1, then the dilution factor is 1/2 because we're taking 1 and doubling it, the volume. Let's say we take 1 part and dilute it to 3 parts total. That's a 1-to-3 dilution. The 1-to-3 dilution, the concentration is going to be 1/3. And so that's going to be times the concentrated solution here. This is a solution dilution problem. And so if we take the, if we look at molarity times volume, let's go back to the original one here. Molarity times volume, what are the units of molarity? Well, the units of molarity are moles per liter, units of volume are liters. So liters times mole per liter gives us moles. So moles initially of solute equals the moles at the end of the solute. So the number of moles don't change, just the volume changes. And so that's what this slide is illustrating here. If you look at the solute, we have 5 solute particles here. And after we still have 5 solute particles, we just diluted it down, added water. So that's where that equation comes from. That equation comes from that. How it's used is like this. We just use dilution factor. This looks like a 1-to what? A 1-to-3 dilution. Do you see that? We started off with 1 part, we end up with 3 parts. So 1-to-3 dilution means it's going to be 1/3 the original concentration. 1/3 the original concentration. So let's see solution dilution in action here. This is a illustration of how we do solution dilution. You can see they have some of the concentrated stuff here of the stock solution. You can have a whole bunch, and then you take some. And so what do they want here? What they want? 100 milliliter volume. This is called a volumetric flask, and this only has 1 line here. that one line is marked and calibrated to 100.0 milliliters. So if I fill it just to this line, it's 100.0. In fact, that's the only volume this measures, 100.0. This is also a volumetric flask. There's a line here, and that line is calibrated for 1,000. And so they're taking 100 and then diluting it to 1,000. If you start off with 100 and dilute it to 1,000, that's a 100 to 1,000 dilution, or in other words, a 1 to 10 dilution. If it's a 1 to 10 dilution, it's going to be 1/10 the original concentration. The original concentration is 0.1. The final concentration is 0.01. See that? So it's a 1 to 10 dilution. Well, how do you do that? In practice, this is how you do it. You know, you use volumetric flasks like this. These volumetric flasks are very expensive. These necks are fragile, so you don't want to break them. And we pour the concentrated in here. We got to make sure we get all the concentrated, so they're just rinsing every last drop of concentrated into the big flask. Once we get it in the big flask, we don't measure how much water we put in there. We just fill it until it hits the 1,000 mark, and then we stop. However many milliliters that is, we don't really care. We just fill it until it hits. We just care about the final volume. Even if you were to measure it out, you know, this is tricky because sometimes the liquid volumes aren't added in. So that's the standard practice for solution dilution. So let's take a look at this. So the commercial hydrochloric, sorry, is only 11.6 molar. How many milliliters of commercial hydrochloric acid, which is 11.6 molar, should be used to prepare 5.50 liters of 0.500 molar hydrochloric acid? So now, this is not just figuring out, you know, what we did a solution dilution. This is figuring out how much we're going to need. And so, in this particular problem, what we do is we have some of this very concentrated. This is called the stock solution. It's like soup stock. You know, how much soup stock are you going to use to make your soup? Well, it depends on how much soup you're making. And so we have our stock solution, which is 11.6 molar. And we can have liters of this stuff. Let's say we have 5 liters. If I have 5 liters of stock solution, doesn't mean I'm going to use all 5 liters of it. And so sometimes it's like a trick question. If you put 5.00 liters stock solution, well, you aren't going to use all that. But what we want to do is we want to take some of this stock solution and then put it into a 5.50 liter container. So this is going to be 5.50 liters at 0.500 molar. And so what's missing here? Well, what's missing here is the volume. We don't know what the volume of the concentrated is. And so to figure out the volume of the concentrated is going to equal the molarity of the dilute over the molarity of the concentrated times the volume of the dilute. So here we have this factor here. This is the concentration factor. The molarity of the dilute is 0.500. The molarity of the concentrated is 11.6. Times the volume of the dilute, which is 5.5 liters. So the molarities cancel. We're left with 5.50 liters. Let's see what the book. See what they get in the book here. .237 liters. 0.237 liters is 237 milliliters. So we would have gotten 0.237 liters, which is equal to 237 milliliters. I would have done one extra digit there. So let's see. It counts out to 0.5. That's 5.5. Divided by 11.6. 0.2370. Carry one extra digit and then round it off. So what we're going to do is we're going to take, we got to make sure we have at least 237 milliliters of this. If we only had 100 milliliters, then that's not enough. And so we need lots of stock solutions. So we'll take 237 milliliters of stock solution and then dilute it to 5.5 liters by adding water. Does that make sense? That's what I do. This is solution. It's very useful for lab. Okay. Then once we have the solutions in the correct concentrations, then we do our reactions. We don't want to use the commercial concentrate stuff usually for our reaction. And so we're going to do stoichiometry using solutions here. This is our stoichiometry map. So with molarity, it's easy. With molarity, we can go from the volume of solution straight to the moles. And so we can do a volume to mole, like gases too, but we just need to know the molarity. And so let's take a look at this problem here. Calculate the volume in milliliters of 0.842 molar sodium hydroxide required to precipitate as copper 2 hydroxide all of the copper ions in 30.0 milliliters of 0.635 molar copper 2 sulfate. So what are we reacting here? What's the equation for this reaction? Well, it's going to be is sodium hydroxide a reactant or a product? Yeah, sodium hydroxide is a reactant. Copper 2 hydroxide a reactant or product? I heard both, but what is it? Is it reactant or product? Yeah, copper 2 hydroxide is a product. It's going to be precipitate. Product, precipitate. Copper 2 sulfate? Reactant. So we need to know how to do the formulas for these. What's the missing product? Sodium sulfate. What's the formula for sodium sulfate? Okay. Is it aqueous or solid or gas? Well, all sodium salts are soluble, so it's aqueous. And then we need to balance this. Yeah, 2 sodium hydroxides and it's balanced. So this would be the balance chemical equation. And so what we want is the volume in milliliters of sodium hydroxide. And so what we're after is the volume of sodium hydroxide solution. That's what we're after. But, we're going to have to do this. We're going to have moles of sodium hydroxide. And so we'll be there. And then we have moles of copper 2 sulfate here. So moles CuSO4. So we're going to go do a mole-to-mole conversion. And then we have 30 milliliters of copper 2 sulfate solution. So we have 30.0 milliliters of copper 2 sulfate solution. So with molarity, molarity is moles per liter. And so all we need to know is how many liters of solution we have, and then we can figure out how many moles directly. And so here, if I know the volume and I know the molarity, I can get the moles. So here's the volume, it's just not in liters. So we'll go from milliliters to liters, and then from liters straight to moles. We can go straight to moles because of the definition of molarity. It's 0.635 moles of pure copper 2 sulfate for every liter of copper 2 sulfate solution. That's what we'll use there. And then if we have moles of sodium hydroxide, well, that's a solution too. We could go straight to volume here. That is, we can go from moles to liters if we know the molarity. And we do know the molarity. That is, I'm going to flip over the molarity. It's 1 liter contains 0.842 moles. 0.842 moles of pure sodium hydroxide. This is a liter of sodium hydroxide solution. And so I'm going to just take the molarity and flip it upside down here. So I could do a mole to liter conversion here, liter to mole conversion. Okay, and then what we'll do is we'll just string it all together as a dimensional analysis problem. It's 30.0 milliliters of copper 2 sulfate solution mixture. And then convert it to liters. So 1 liter contains 1,000 milliliters. And then convert it to moles, 0.635 moles of pure CuSO4 per liter of CuSO4 solution. Okay, and then do a mole-to-mole conversion here. It looks like a 2-to-1 mole ratio. 2 moles of sodium hydroxide for every 1 mole of copper 2 sulfate. So 2 moles of sodium hydroxide for every 1 mole of copper 2 sulfate. Okay, then if we have moles, then we can go straight to liters of solution. And that is 1 liter of sodium hydroxide solution contains 0.842 moles of pure sodium hydroxide. And then we want to go to milliliters. So 1,000 milliliters per liter. That should give it to us. Everything should cancel. Milliliters of sodium hydroxide, cancel, liters, copper 2 sulfate, moles of copper 2 sulfates, moles of sodium hydroxide, liters, get converted to milliliters here. Okay, the 1,000 cancels out the 1,000 here. So let's go ahead and do the calculation. It would be 30 times 0.635 times 2 divided by 0.842 equals 45.24 milliliters. 45.24 milliliters of sodium hydroxide solution. And that's what they got, 45.2 milliliters. Well, we did titration lab already. Just a review. For titration, we use burettes and indicators. We use the indicator phenolphthalein. That's the basic titration, but there are other indicators depending on the titration we're doing. Does this look familiar? Yeah, except this is Chem 1A style. Chem 1A style, you only have 1 burette, not 2. Chem 1A, if you overshoot this endpoint, you toss it and start over. So it's less forgiving. So it's harder to get 3 good runs. You're going to have to do the exact same titration in Chem 1A, except you can't back titrate it. You know? Like for example, if we overshot, we can just back titrate it using acid. But if you overshoot in 1A, you're out of luck. You can't back titrate. But that's okay, because by then you should have more skills. These are some terms used in titration. Primary standard. Primary standards are very important. Primary standards are like the kilogram mass. You know, how do you know what a kilogram is? How do you know if you're really getting 1 kilogram? Well, there's got to be a primary standard. That primary standard is going to be the 1 kilogram mass. And so we have primary standards. Well, we have primary standards for chemicals too. You know, primary standard sodium hydroxide would be very pure sodium hydroxide. But it doesn't have to be a solid. Sodium hydroxide is very hard to get pure, right? Because sodium hydroxide is chemically reactive. So it's hard to get it. It reacts with air. That is, it reacts with the CO2 in air, forms sodium carbonate. It reacts with water in air, form aqueous sodium hydroxide. Sodium hydroxide is normally a solid. And so it's not a very good primary standard. We look for better primary standards, ones that are stable and that you can get to high purity. Those are primary standards. And then we compare other things to that. And so in titration, oftentimes what we'll do is we'll do standardization. Standardization is to determine the concentration of a solution by titrating against the primary standard. Well, the primary standard that you used was the HCl. You know, although it's not really a primary standard, it was more of a secondary standard. Because the HCl itself was standardized. Let's say this is just stoichiometry. This is stoichiometry with a different goal, you know, than this. So let's take a look at this problem. A 25.0 milliliter sample of an electroplating solution is analyzed for its sulfuric acid concentration. It takes 46.8 milliliters of the 0.661 molar sodium hydroxide to neutralize this sample. Find the molarity of the acid. All right, so sulfuric acid, what's the formula? Plus sodium hydroxide, NaOH. What does this produce? Sodium sulfate and water. So let's go ahead and balance this. Water is liquid. Okay, how should I balance this? Just tell me the coefficients here. 1, 2, 1, 1. And it turns out this has got to be 2 here, otherwise we don't have enough hydrogens to do it. Altogether we need 4 hydrogens, 2 here and 2 here. The other way of thinking about it is we're taking a hydrogen and a hydroxide. A hydrogen and a hydroxide makes water. A hydrogen and a hydroxide makes water. We have 2 hydrogens and 2 hydroxides. 2 hydrogens and 2 hydroxides makes 2 water. Let's see it that way too. All right, so you know the stoichiometry is kind of the same. Okay, so what we have here is what are we given? We're given 46.8 milliliters of 0.661 molar sodium hydroxide. So we have 46.8 milliliters of sodium hydroxide solution. We're also given 25.0 milliliters. I don't know. Is it 25.0 milliliters of sulfuric acid solution? Yeah, it looks like that. We're also given 25.0 milliliters of sulfuric acid solution. And so what do they want us to find? They want us to find the molarity of sulfuric acid. The molarity of the sulfuric acid is going to equal the mole of H2SO4 divided by the liters of H2SO4 solution. So we want the moles of pure H2SO4 divided by the liters of H2SO4 mixture. Well, that's this. The H2SO4 solution is here. Because we don't know the molarity. In order to go from volume to moles, we need to know the molarity. But the molarity is what we're solving for. And so this doesn't really belong here. This belongs over here. plug it in here. And so this is going to be 0.025 liters, just converted into liters. Here, go to 3 sig. We need one more zero. But we're given the molarity of this. If we know the molarity of the sodium hydroxide, we could figure out how many moles. So we'll go from milliliters to liters, and from liters to straight to moles of sodium hydroxide. And from moles of sodium hydroxide, we're going to go to moles of H2SO4. And then from moles of H2SO4, that's the missing part here. That's what we need there. So we have two choices. One, we can just do the separate calculations, or we can just combine it into one. What do you want to do? Do you want to combine it into one equation, or do two separate calculations? Let's do it separate? All right. And so to figure out the first part, the top part here, we're going to just use stoichiometry. That is, we're going to start off with our given 46.8 milliliters of sodium hydroxide solution. And then go to liters. So here it's going to be liters, 1,000 milliliters. So we got liters of sodium hydroxide solution. And then from liters of sodium hydroxide, we can go to moles of sodium hydroxide if we know the molarity. The molarity is 0.661. And so this is 0.661 moles of pure sodium hydroxide for every liter of sodium hydroxide solution. So now I'm at moles of sodium hydroxide. For moles of sodium hydroxide, I can just go straight to moles of H2SO4 because it's a 1:2 ratio. 1 mole of H2SO4 for every 2 moles of sodium hydroxide that react. And so let's just go ahead and plug everything in there together. We're going to do the top calculation first. 46.8 divided by 1,000. Times 0.661 divided by 2. Here, I don't want to round this because I don't want too much round off here. So I'm going to just do 0.0154674. Just carry all the digits in the calculator. This is going to be moles of H2SO4 divided by this 0.0250 liters, which we did the calculation just by moving the decimal place 3 over. And so I'm not going to clear this, I'm just going to do it divided by 0.025. And that gives me 0.6186 molar H2SO4. And so what we had was an unknown concentration. And that unknown concentration, what didn't we know about it? Well, we didn't know the moles. We knew the volume. The volume was given. The moles, however, weren't, and we had to use stoichiometry to get the moles. So let's see how they do it. They did it as two separate calculations. First, they calculate the moles of H2SO4. They rounded it to 0.0155. And then they divided it by the liters of solution. And so they got 0.620. They got 0.620 because they did it a intermediate rounding step. We would have gotten 0.619 as our answer. And so titrations, we typically are looking for an unknown concentration. Unknown concentration, we use stoichiometry to figure out the moles, and we're given the liters. Where are we given the liters from? The burette. The burette is going to give us the liters. And so that has to be determined experimentally. We aren't going to do titrations with normality, so skip normality. Okay, do you remember colligative properties that I mentioned a little bit ago? For colligative properties, then we have to use something called molality. You recall what the definition of molality is? moles of solute per kilogram of what? Solvent, yeah. And so we need to do that here. So what happens is this. You know what pure water, what temperature pure water freezes at? 0 degrees C. Do you know what temperature salt water freezes at? A lower temperature, higher temperature, or the same temperature? It turns out salt water freezes at a lower temperature. Even like soda water freezes at a lower temperature. You might have this. You might have a very cold freezer, and you open a bottle of soda and put it back in there, and it completely freezes. It freezes right when you open the bottle because the CO2 escapes. And it depends on the concentration. The more concentrated it is, the bigger the difference in the freezing point. And this is called freezing point depression. The freezing point is going to be depressed by delta T. The equation for that is very simple, to calculate. It's K times molality, where K is the freezing point depression constant. We just get that from a book. It's the molal freezing point depression constant because we're using molality here. And so let's take a look at a calculation here. What happens is, okay, what this slide is showing is it's showing this dye is not dispersed here. The dye is in the center here, and on the edges is pure water. The pure water freezes at 0, but the center is not frozen yet. The center is not frozen because the dye is screwing up the crystal. We talked about nucleation and growth yesterday. If you have all these solvent particles in here, is it going to be easy to nucleate and grow crystals? No. And so these are going to inhibit nucleation and growth. That's one way of explaining freezing point depression. There's other ways of explaining this as well. And therefore it's going to freeze at lower temperature to get that order in there. It's probably going to freeze out separately. Like, it's too hard to incorporate the dye into the ice crystals. They're going to separate. All right, determine the freezing point of a solution that is 12.0 grams of urea in 2.50 times 10 squared grams of water. And so we have 250 grams of urea water. Or, no, that's not even right. That's 250 grams, not of solution, but of just pure water. Water in this case is a solvent. And so when we're dealing with molality, numbers are a bit tricky. As we got to shift our thinking a little bit. And so we got 12.0 grams of urea. And this is our solute. And then we have 250 grams of water. This is our solvent. And so altogether, we have 262 grams of solution. Because the solute plus the solvent equals a solution. So 262 grams of solution. Well, they want the freezing point. And so what we do is we do this delta TF calculation, delta TF. Delta TF is equal to KF times M. And so we look this up in a table. And then we have to calculate this. All right, so let's go ahead and calculate what is the molality of this. The molality of this is equal to the moles of urea divided by the kilograms of water. And so the molality is equal to the moles of urea divided by the kilograms of water, water being the solvent here. And so the moles of urea we're just going to get from molar mass dimensional analysis. So urea consists of 1 carbon, which is 1201, oxygen, which is a 1600, 4 hydrogens, which will be a 404, and 2 nitrogens, which will be a 2802. So just add those up: 6, 7, 0, 8, 12, 20, 4, 6007. And so the moles of urea are going to come from this. We have 12.0 grams of urea, and the molar mass is, for every mole, 1 mole of urea, we have 60.07 grams of urea. And the kilograms of water is going to come from here. We have 250 grams is 0.250 kilograms of water. You can just plug those in. Yeah. And then get the molality. So it comes out to 0.200 moles divided by the 250 grams, which is 0.250 kilograms. I skipped this setup here. I just converted it straight, which gives us 0.800 molal urea. Then we have to look this up. KF. KF, if we look it up in the table, it's 1.86 degrees for every molal. So what that means is this: for every molal, the temperature drops by 2 degrees. And so water normally freezes 0 degrees. If you have 1 molal, a little bit more than 1 molal, it's going to freeze at -2. 2 molal, it's going to freeze at -4. 3 molal, it's going to freeze at about -6. That's how this works. And so this 0.8 molal is going to be 1.49 with going delta. And so here's 0, we're going to be 1.49 below it, so it's going to freeze at -1.49 degrees C. And so we take our normal freezing point and then minus the delta T F, we get -1.49. It doesn't have to be water. Water has 1.86 degrees C per molal. Other solvents have different KFs, so that's why we have to look those up in the table. But water being the most common, this is done. The other colligative property is this. Pure water boils at 100 degrees C, but salt water, does salt water boil at 100 degrees C? No, salt water boils at a higher temperature or lower temperature? At a higher temperature. And so this is how we keep track of these things. It's boiling point elevation, freezing point depression. And so they get farther this way. You look at the equation is very similar. We just need the molality in KB. KB is about half a degree per molal. Let's see what this is for benzene. For water, it's about half a degree. In fact, let's just do for urea. So urea freezes at -1.49. What does this urea solution boil at? And so I'm going to get the KF value of the table here. And so I need, or KB for water BP. The KB value is 0.512. Let's see, this is a reliable source. It is, because I know the number. It's 0.512. And so the calculation is going to look like this. So let's go ahead and get that molality. What was that molality once again? Let me just double check their calculation because I don't like the way they round. So I'm going to do 12 divided by 60.07 divided by 0.25. I get 0.7990 molal, which is pretty close. I got 0.800. And so delta TB is just equal to KB times M. Well, KB is 0.512 degrees C per mole. And we have half a mole, 0.8 tenths of a mole, 0.77990 mole. So what does that come out to? 0.512 times 0.799, which gives us 0.409. And so that means the boiling point is going to be, it's elevated, so it's going to be 100 plus delta TV, which means it's going to be 100.409 degrees C. So the boiling point is elevated about half a degree. Freezing point is depressed by about 1.5 degrees. Okay, I'm going to stop here and then we'll take a break and start again.